Hello and welcome to the Winter 2026 Quarterly Projects Workshop on Arduinos. So first of all, I'll go over basic circuitry and then basic breadboarding and the basic premise on how Arduino coding works, and then some stuff about making circuit diagrams for when you do need to make diagrams and documentation for your project submissions. Alright, so this will be a very basic and surface level tutorial on everything. So first of all, introduction to circuits. Breadboards, they give you a quick way to connecting these together for quick prototyping. They're not the best for production hardware because the wires can get loose very quickly and some of the rails are not very consistent. So that's where printed circuit boards or PCBs come in. However, I will not be covering them in this specific workshop. If you do want some knowledge on that, I can also make a PCB design workshop in the future if requested. And each component does something different. So, and they work together to make a really cool circuit that functions and does some cool stuff. And also, Google and datasheets are your best friends because they give you all the information about what a component does, how you use it, what you're supposed to pair with them, and etc. So first of all, how does a breadboard work? So a breadboard is just a little plastic board that you can find in most electronics labs, and here's a transparent one on the left so that you can see what they usually look like, but the more common ones are on the right where it's just opaque. And when you rip off the bottom tape on them, you'll find little metal rails, and as long as the metal rails are connected, your electrons can flow. So you always want metal on metal contact when you are building a circuit. And usually when you peel off the little pad thing, you'll just find no metal contacts. And if you are ever wondering how these holes are connected together, you can just refer to how the little metal strips are connected together, so you know, oh, one wire from A27 connects to E27 because the metal end of the wire goes through the metal strip on the breadboard and then out to the other metal wire end. So there you go, it's a complete circuit. And then the power rails are usually, by convention, used for power. So a battery or the ground or the negative end. So yeah. And here's a just more graphical representation of how things are connected together. And here's an example of a breadboard circuit from a solar panel project. And here's an example from a swimming plant project, which I co-authored. So yeah, these are way more complex circuits, but I will be covering some of the concepts in a later slide. So when transitioning from breadboards to schematics, you won't see exactly where to connect each wire into a hole. You will just see where something is connected together. So in this example, you see that IO46 is connected to a resistor and then to an LED to ground. So what you have is IO46 to an LED to a resistor to ground. However, since resistors are non-polar, you can just put them either in front or behind the LED, but the LED is direct. So direction does matter on an LED, so that's why you make sure that the long leg and the short leg are in the correct orientation, but I will describe more details on that on a later slide. Alright, so a basic circuit is just a source, so that could be your microcontroller, a battery, the wall outlet if you are working with AC power, and then some loads that pull from the source. And then since all circuits need to be closed, that's one of the fundamental ideas of a circuit is that it needs to be closed so that electrons can flow from one side to the other side. It has to have a complete loop, so you have to go from the source and end at the source, or alternatively go from a positive end and to a negative end. So that's why the metal is important, so that you can complete the circuit. Alright, so some basic circuit components would be some diodes, which are, you can think of them as one-way valves. And then capacitor is just to store some electrical charge, and then inductors resist changes in current, and then some resistors restrict the flow of current, so if you want your current to lower. Some DC voltage source, that would be typically your battery or just direct current, and AC voltage battery, that's most commonly found in wall outlets, but you can also do some other alternating current stuff like using a pendulum and etc. But those are some more unique circumstances that I will not be covering in this slide. Alright, so resistors are very common in circuits, but have you ever wondered how you find the value of them? It's by using a chart like this, where you can read the value of it. So the more resistance, so the higher the value, the more it will restrict the current and make your current go lower. So you can see how you can read a 4-band resistor and also a 5-band resistor in this picture. Alright, for buttons and switches, these are also very common, and you usually connect the opposite legs for a button in a diagonal pattern from top to bottom. So top left connects with top left connects with bottom right, and then top right connects with bottom left. And when you press a button, those two finally get closed, so that current can go through. But you can also do top left and bottom left, or top right and bottom right, and you can get those to always connect. Alright, for switches, you see how it's a sliding mechanism where 1 and 2 are connected together when you slide the handle to the left, or 2 and 3 are connected when you slide the handle to the right. So if you want to make an on and off switch, you would probably just put one leg or one side of it to 1 and the other side of it to 2, and when you slide the handle over to connect 2 and 3, one is now disconnected. So since one is disconnected, the circuit is no longer closed and it's broken now, so no current will flow through, and hence you have an on-off switch now. So you slide over to 2 and 3, neither 1 and 2 are connected together anymore, so you have an off. But when you slide it back, 1 and 2 are now connected again through the metal part of the handle, and there you go, you have an on. Alright, for voltage regulators, I'll just quickly go through a bunch of these little components, but they usually do some sort of regulation, or just converting a higher voltage into a lower voltage. So you can read more about it in this datasheet link, and I'll also be linking these slides to the description of this video, so you can also look at it there. But you will also see what the circuit looks like inside the little datasheet, and also what each leg is supposed to do in the diagrams. Same with op amps, except they amplify signals, and logic gates. They're usually packaged in the IC or integrated circuit packages, and they usually give your circuit some logical behaviors, and I'll explain what logic usually is. So in this case, I have AND and OR. There's also XOR, there's also NAND, and etc. But you can look up those charts online if you would like. But this is how it usually goes. 0 just means no current or no power. So 0 and 0 on the two terminals would be a 0 on the AND gate, and also a 0 on the OR gate, and so on. 0 and 1, you got a 0 on the AND. But if you hooked up that same configuration to an OR gate, it'll be a 1, and etc. So you can review this chart, and you can also look up other charts for other logic gates. So pinout diagrams. These allow you to understand how a component is wired up. Well, not exactly how the internals work, but you know what each pin can connect to on an Arduino so that you can control the module. So they are usually what you will be doing in QP, since you're not going to be building these from scratch. It'll take way too long, and it'll take more than a quarter. So usually you just slap together multiple modules into an Arduino and hook them up to get them to connect and do your desired function. So the DF Mini Player is an example that I had earlier. It was from the Screaming Plant project, and I used the RX and TX pins, the VCC for power, the busy pin for maintaining whether or not the module is busy, GND for ground, and etc. So you'll find a lot of guides that tell you what pin to connect to, and you can follow those guides to understand more about what the component pinouts do. Alright, so time to learn how programming in Arduino usually works. You can go to arduino.cc.en or /en/software, and you can get the Mac or Windows, or if you are on Linux, you can get the download for that. And you can also get the command line version if you prefer command line instead. But usually for beginners, that's the target audience of this presentation. The IDE, the integrated development environment, is usually the way to go. Alright, so what does a program do? It's just a set of instructions that tells your microcontroller or your computer, or in this case in Arduino, what to do. So it processes an input, performs some sort of computation, and then produces an output. So let's say an input is you pressing a button, and then it does some calculations in the back saying, oh, if you press a button for this long, I should set the LED to this amount of brightness, etc. And here's an example from the Arduino documentation. Arduino docs will be also your best friend because it'll provide a lot of examples for how you should structure your code, how to write them, also what libraries to use to interface with specific modules, like I explained earlier. So yeah. So in Arduino, it's C++ with some tweaks to make it more approachable for beginners. You don't need destructors, pointers, and other stuff for your basic of blinking an LED or measuring light or detecting how much moisture is in the air, or looking at how much soil, or looking at the weight of something. So yeah. And then program files in Arduino IDE are called sketches with a custom header file and etc. But the custom header files and other more advanced stuff are outside the scope of this workshop. If you want to learn those, I'm pretty sure there are guides, or I can help you out if you request it. Usually these sketches have a void setup and a void loop. However, you can declare functions outside of those two, and you can do some very aggressive optimizations where you write your own functions and make the compiler optimize away your setup and loop. But if you know how to do that, then you probably should click off this presentation, since you are pretty well set up for how to use Arduino. Alright, so for comments, they're for human consumption only, and when you compile your code, which is doing the check mark button in the Arduino IDE, they get removed from your code and then turned into machine code that a computer can read. So these are how you would structure a comment with the 2 slashes, or if you want to comment multiple lines, you have to do the slash asterisk. So the next key concept would be a variable. They are basically storage locations that hold data or values. So the structure of it would be your data type, so what type of data you're trying to hold, the name of it, so you can just name it anything you want, and the data that you want to put inside of it. And the bucket analogy is used a lot, which is when you, for example, make a bucket size of 20, the label is your integer, so the type of data you're trying to hold is an int, and then you have your bucket size, which is the name of your variable, and then you have 20, which is the thing that you want to put inside. And usually ints are 4 bytes long, and that's why you need to specify the variable type, because different types of variables are different sizes. So that's why you need to give the compiler a heads up on what you're trying to store so it can allocate enough space to hold your data. In other programming languages like Python, the compiler handles that for you. However, in C, it's a little bit faster because the compiler does not have to go figure out what you put in here. You can just straight up read off your label and allocate that amount of space. Alright, so some data types that are common are ints, which are integers or your whole numbers, floats, which are your decimals, chars, which are single characters, bools, which are your true and falses, or boolean. And an example would be the bucket size. And if you want another way to think about it, a bucket size, the name of the variable, they're just like variables in high school algebra. So x equals 4 or y equals 4x and stuff like that. And different data types consume different amounts of memory, as I was saying earlier. And you cannot divide 41 by a boolean true. You can do that in JavaScript, which I will show you in a GitHub workshop later on. And consts are just values that you don't want to change. And hashtag define, that's called constant propagation. And it's basically normally faster because you don't have to wait until all your code loads into your Arduino to set the values. And it's a common optimization technique. And you can read more about the constant propagation optimization technique as well. And there's also double, which is a bit more precise than floats. So if you need that extra precision, use a double. So some key takeaways, here's some examples of how variables are declared. Alright, so next up would be conditional statements, your if, else, if, and else. And these you can make ladders out of, what people usually call them. And it allows programs to make decisions based on conditions. And you execute specific blocks based on if it's a true or false or binary 0 or 1 condition. And here are the comparators, so greater than, less than, equal to, or greater than or equal to, or less than and equal to. Here's a note: a single equal is for assigning variables, a double equals is for comparing. So do not use single equals if you're trying to do if something's equal to another thing. Make sure to do double equals. There's also triple equals, but that's for JavaScript and other languages, and that's not for C++, so yeah. Alright, so for booleans and conditions, you can pause and try to work it out. So is 4, so just think about if this is true or false, and the hint would be to say it out loud in English or whatever language you speak. Yes, that's a 1, so that's a true. Alright, so you have y equals 4. How about this? Yep, that is a false, so that's a binary 0. How about this? Alright, that is a true or binary 1. Alright, so how conditional statements are formatted: you do if a condition, and then you do the curly brackets, and then you put in the code that you want to execute if a condition is true inside the little block in here. And then else if, that's if this this new condition is true. However, the previous condition was not true. So that's why it's called a ladder, because you climb the first one, the first if. Oh, that's not true. Let me go down to the else if. Oh, that's not true either. Now you go to the else, and that's just a condition if everything else above it is false. Hence, it's called an else. So you can have super long if else ifs. So you can do if something happens or it doesn't happen, so it goes in else if. If that doesn't happen either, you can go to another else if. If that doesn't happen either, you can go to another else if, and so on until you reach an else. Or if you don't want anything to happen at all, you can just skip the else and go move on with your other code. Alright, so this would be an example of the if, else if, and else ladder. And you can try this out on your own machine since you have Arduino probably downloaded by now. So make sure to put serial.begin 9600 inside your void setup, and then you can run this in your void loop. So you set the age as 20, and then if your age is bigger than or equal to 21, you can vote and drink. And then you can also do an else if, or you can vote, or else you are a minor, and you can copy this code into your own machine and try it out. Alright, moving on. So conditions with logical operators. So just like the logic gates slide previously, you have your ands, ors, nots. However, you do not use and, you use the double ampersand or double and sign. You do the double pipes or double lines for or, and then not, you use the exclamation mark. So I will give some examples and feel free to pause to think about them. Alright, that is a 1, that is true. How about this one? That's a 0, so that's a false. And that's also false. Alright. So, adding on to the example that you probably finished running on your own machine, let's add this Boolean can drive feature. You can add on to your existing code that you have pulled up, and let me know how this goes. Alright, so here's the full code if you would like to add it to your existing. Alright, so do you notice a problem with the if else if ladder? So if condition 1, then you have else if condition 2, then you have else if condition 3, and etc. until you reach an else. This could get very long and very tedious if you're doing a very long decision tree. So you have switch cases, and you don't need to use them if else ladders work fine. However, they just clean up your code and make your code look nicer. So you declare of a switch, and then you put your variable, and then you put all the cases where the variable could go into. So this is limited to a variable that has several different cases. So if you are trying to compare different things between each if and else if statement, then this does not work very well, and you have to put a break at the end to prevent the switch case from falling through, which happens when you do case label 1. You do your code, which is in the slash statements, and if there's no break, it'll just go and run case 2 anyways. Alright, so here's an example of switch cases. It's a very abstract example because I did not have any example code coming in, but it should serve the purpose of giving you all a idea of what happens. So switch my mood, which is a variable, and then in the case that's happy, play the happy playlist. and I'll show you how functions work in a later slide, which is what this is, where you play happy music and then you have these two parentheses, and then you break. In the case that it's sad, you play sad music, break, and then on default you just play some beam music. Alright, loops. So these are very important because you can repeat code that you do not want to keep copy and pasting. It's pretty nice to not be able to copy and paste to loop code. So you have two types. You have your while loops and your for loops. And here's the structure for both of them. And for the for loops, the little bracket slash thing, that's not actually what you write. You put either less than or a greater than, or any of the other comparators, like less than or equal to, or greater than or equal to. And for the I++ or I-, those are called iteration, which is the same thing as I equals I plus 1 for the I++, and then for I-, would be the same thing as I equals I minus 1. So it's basically I, which is your new I, is equal to the previous I minus 1. Or in the case of the plus, it would be your new variable is equal to the previous iteration of your variable, adding a 1. And I'll show you an example of this when I get to the functions section. Alright, so an example of a while loop. So you would set your count as 0, and then while the count is less than 3, you just print out the count, and then every single time you set the count as the previous count plus 1. You can try this out on your own machine as well. Alright, moving on to the for loops, you have your initialization. So similar to the while loop, you have your count set to 0 initially, and then while your count is less than 3, your count adds 1 to itself. And then each time you run your for loop, it prints out your count. So how this is interpreted is, for you start out with your count is equal to 0, and then while your count is less than 3, your count should add 1 to itself, and then it should print out count. And you can try this out in your void loop as well. Alright, for nested loops, it's basically where you can have a loop inside of a loop. And here's an example. It's an abstract example of someone eating food. So while the day is not ended, so remember the exclamation mark means not. And then while the day is not ended, for initially your I is 0, and then while I is less than 2, you should increment your I and eat food. And then once you're done eating your food, you add 1 to your hour, and then if your hour is at 24, you reset your hour to 0, and then you set your day to ended. And since the day is ended now, the while loop is no longer true, so the while loop stops, and you can move on to your next pieces of code. Alright, so for arrays, they're basically a collection of elements of the same data type. And just think of them as a way to organize and manage related data very efficiently, since you can just stack them next to each other, and that's how they're usually set in the storage anyways. And just think of them as a shopping list. And a keynote is that the indexes or indices start at 0, except for if you're doing MATLAB, which starts at 1, and there's some other languages that do other strange things as well. Alright, so for arrays, there's 3 ways to initialize them, or 3 ways to set them up. So you set the data type and then the name, and then you use the square bracket to set the size. Or you can set the data type, the name, and then you use the square brackets. Instead of putting a size in there, you can just set it equal to curly brackets and use directly put all the elements you want to put in the array. Or you can do a hybrid method where you can do a data type, the name, you set the size, and then you put all your elements in there. So an example would be int my array, and I set the size as 3. So I set it as my array. I index 0, so I get the first thing, and set the first thing equal to 3. And then I set the second thing, which is index 1. Remember, indexes start at 0, and set that equal to 4. And then I get the third thing, and set that equal to 7. So what does my array contain now? You may pause the video. It should be pretty quick. Alright, so for functions, like I alluded to earlier, they promote code organization, reusability, or modularity, and also makes your code more readable. They break your complex tasks into smaller and more manageable parts. So if you have a long list of instructions, you can part those out and chop them up so that you can do them function by function. So instead of doing one instruction at a time, you can just have a function do a chunk of 3 or a chunk of 4 or a complex loop that goes into another thing. So you can do a while loop that calls another function, and that function can hop to something else. So you can chain different pieces of code together in more complicated ways by using functions. There are two types of functions, which are user-defined, so those are the functions you write, and then library, which are just other people writing functions, and you just take those functions and slap it in your code. So basically, using library means you don't have to rewrite a function that someone else made. You can just straight up use someone else's function. Alright, so functions are usually declared using a return type, the name of your function, and then you put your parameters. And parameters are basically the inputs of your function. So what do you want your function to know when it computes some stuff here? So you may want your function to know what the previous light level was, or how heavy your current object is, or what the sensor is currently reading, or what the past 3 values in an array of values that your sensor read. So you can pass in pretty much any type of data into the parameter, and when you call your function, you would just put those parameters in as an input. You're basically writing blueprints using functions. And then an example of how libraries would work would be the hashtag include, and then you put your library name. You can refer to the Arduino documentation to know what most of the libraries are. And when you include the library, you get access to all of its functions, and you can straight up call those functions without having to write them yourself. Alright, so an example of a function would be the add 10, which I put the parameter as an input, so that would be a human input or whatever you were using previously. And then it would return, which means it would spit out input plus 10. So whatever input plus 10 is, it would spit it out. So here's how you would call the function and use it. So first I have an integer called goopy, and I set that to 2. And then I set goopy as equal to whatever goopy was before, but add 10. You can try this out. And alternatively, goopy plus equals 10 does the same thing, because goopy plus equal 10 is the same thing as goopy equals goopy plus 10. It's just a more generalized way of doing the plus plus thing, because the plus plus is only adding 1, but if you do plus equals, you can add more versatile numbers. Alright, so some examples of a library function would be the liquid crystal library, which is for LCD displays. And you would initialize them by calling a function. I don't know what this function does. I just know that it takes these certain numbers, and those certain numbers map to pins on your Arduino. However, if you want to know how this function works, you can just go to the Arduino documentation and look up that library and look at what the implementation or how someone wrote the code. And you can set the cursor to index and 0, or you can print out this little rectangle basket thing, or you can set the cursor to a column and 0. So All these functions you can read more about in the Arduino documentation. And then some common Arduino functions that are built in would be serial begin, like the one you used earlier, serial print, like the printing functions that were shown earlier, serial read, which is read whatever the serial monitor is doing, or pin mode, which is setting the mode of your pin, of your actual Arduino pin, to either an input, an output, etc. There's also digital write, which is writing to a digital pin. There's also analog write for analog pins, but I didn't put that on here. You can read all about it on the Arduino docs. Or digital read, which is reading a digital pin. Alright, so if you want to try out the following exercises and you don't have an Arduino board, you can go to an Arduino simulator, such as Tinkercad, and then log in. You can use a personal account, or if UCSD gives you a school account, you can use that as well. You can click create and then select circuits from the drop down menu, just like how it is in the picture in the top right corner. And then once in the workspace, you'll choose the Arduino Uno R3 and then choose a breadboard, and then the necessary components for the exercises will be shown in the next slides. And then you connect wires by clicking the first contact point and then clicking the next contact point. Do not click and drag because that will not work. You can try, but it will not work, so yeah. Alright, let's try the simple LED circuit that I showed earlier in the schematics slide. So here's the code for it, and then the stuff highlighted in yellow is for you to fill in the blank with. I will also link the slides in the description as mentioned earlier so that you can copy and paste the code in, or you can simply type it in manually yourself as well. That'll probably build better muscle memory, I'm not sure. You can pause and do this exercise, but I will move on to the next exercise. Alright, this next exercise uses a button, and do not take apart your previous LED circuit. I repeat, do not take apart your previous LED circuit, because you will be using that alongside with this button circuit. And as usual, you can copy this code and fill in the highlighted yellow blanks. Alright, you can pause to do this exercise, but I will be moving on. Alright, so now try controlling your LED with your keyboard. So here's a function, and if you would like to know how it works, I can explain it further in the comments if you ask a comment or if you just message me. But the key part is to fill in the yellow highlighted blocks and also put some code where I highlighted, put your code to turn on LED, and etc. You can also pause to do this exercise. Alright, so some additional resources that you can look at would be Platform IO. That's the next level up, the more advanced version of Arduino, and you can watch a video on how that works. There's also a beginner electronics course that I thought was pretty good, so there's also this course that you can look at. And if you want to learn more about C++, there's this quick tutorial course that you can watch as well. And then Phil's Lab is very good for just general electrical engineering circuits type of activity, so you can also look at what Phil's Lab is up to. Alright, so let's try some fritzing. What is fritzing? It's a tool for users to draw circuit diagrams with pretty relatively easy methods, and allows users to create their own components as well, as long as you know how to draw them and just import them in as SVG files. Some other tools in similar realms as fritzing would be electrical computer aided design or CAD softwares such as KiCad or Altium or Eagle, PSpice, LTSpice, and whatnot. You also have peer drawing tools like Krita or Google Drawings, Adobe Photoshop. However, fritzing is just nice and easy to just plop down. A few of the university courses that teach circuits actually use fritzing to draw their diagrams. So fritzing is just a nice tool to draw your circuits when you want to document something for submission. Alright, so how you access fritzing? You just come to the slides, click on the Windows download or the Mac OS download, or if you're on Linux, try Wine. I don't know, good luck, have fun. Alright, so a live demonstration of how fritzing works. Alright, so once you load up fritzing, you'll see something like this. And when you're doing a breadboard or a schematic, you'll just go to the tabs at the top and you'll see breadboard, and you can click on it to get a breadboard, or you can click on a schematic and start placing your components down. So let's just create a simple component. First, I will just go to Core and go to the search menu and put down an Arduino Nano. Let's see. This one looks good. Oh, that's the schematic. I'll go to the breadboard so it's more noticeable. Alright, so this one looks good, right? Alright, let's go to an not LCD, let's OLED. Oops, hold on. What? Oh, there you go. Alright, so an OLED screen. And we will just go and connect these up. First of all, I'm going to rotate this with Command R for Mac, or Control R for Windows. And let me just snap these on. And you see how it's highlighted green where these pins are connected to? I will also go and grab this Arduino and rotate it with Command R. And snap it right on here. And now these are all connected. Alright, let's start wiring. So let me close out the search menu, go back to Core, and before I start wiring, I can show you that there's a plethora of parts, and if you don't find a part that suits your needs, you can just go on Google and Google a fritzing part for it. For example, this specific OLED panel was not inside fritzing. I had to go download the FPZ file, and you can just double click the file and it'll get automatically imported into fritzing. It's just so nice, so user friendly. Alright, so first of all, let's connect these components up. So you have ground, which usually goes to ground, and you have VDD, which usually goes to the red rail for power. And then on the Arduino side, you have your 5 volts that you can just put down to the red. And you have your ground, which goes to your ground. There you go. And now you can go to SCK, and your SCK for my example, I would just put it to A5, and this would change depending on how you configure it in your code. So, but in my specific example, I'll put it to A5, and for the SDA, I'll put it to A4. Now, you see how all these wires are the same color, and it's pretty hard to differentiate between them. So, by convention, the grounds are black wires, so you can just click on the wire, and then on the right panel, near the middle to the bottom, you will see that there's a color changer. You just click on that and go to, there should be a black here. Yep, see it. Yep, you can just change that to black, and then for the other ground wire, you can do the same thing and change it to black. Alright, so for the power rail, it's usually convention to click on, oops, I think I clicked on the board. Yeah, click on here and change this to red. And go to here and change it to the drop down to red. All right, and you see how some of these wires are overlapping? What you can do is hold Control or hold Command if you're on Mac, and click and drag the wire down. You see how it's nice now, and you can let go whenever you're happy, and you see how this wire is no longer overlapping with the other wire. If you want to do some crazy shapes, you can move your cursor up on the wire, hold Control again, or Command if you're a Mac, and click and drag it, and now you can do fun shapes like this. And let me add another breakpoint like this, and here, and here. Yeah. However, that's besides the point. I will do Command Z or Control Z to undo it and just pull it back down to here. And since this is still overlapping, I can just do Control or hold Command and drag it up here. And there you go. It looks a little bit nicer and more clear. However, you can definitely do a better job and make it look way nicer. But since they're the same color, it's nice to differentiate them, so I'll just assign this one to green, sure. And now you can see clearly which one connects to which. And here's a nice trick. If you don't like all this green highlighted thing, you can just do File at the top, and you can do Export, and you can do as an image, and you can save it as your standard PNG or JPG or SVG. I don't think you can see it on the recording, but just go to File, Export as an image, and you'll see a drop down of PNG, JPG, SVG, or PDF. It should be on your top bar. If you're on Mac, it will be at the very top, or if you're on Windows, it should be next to where the exit and minimize buttons are. So yeah, and what you can do is export as an SVG, or if you are happy with the result, you can just export as a PNG or a PDF. And I will save it really quickly to my downloads. Alright, so I have Inkscape open, and the other SVG editor works as well, but I prefer Inkscape because it's nice to just nice to laser cut on. So let me zoom in. So this is what you would see if you click on a new document. Alright, so what you would do is File, Import, or you can do Control I or Command I, depending on if you're on Windows or Mac. And then you can just import in your file. Okay. Oh, yeah, so you see how it's an entire SVG file? If you don't like, oops. So you can just double click on this component. It seems I added an extra Arduino by accident, so you can just clear it out by just double clicking it and then tapping backspace or delete, and there you go, it's gone. If you don't like the little watermark at the bottom, just double click on it and delete. Now it's gone. And if you want to emphasize one part, let's say you want to emphasize the OLED screen, but all this other stuff is stealing other people's attention away, so you can just do click it. Oh. So you can just hold Shift and click, 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 and click all the stuff that you don't want to be emphasized. And you can click these wires and these wires, and you can just go over to transparency and change it. So on the right side panel, you can just go to opacity at the bottom right corner, and you can just lower it, and there you go. It's now less obvious. So now you can just emphasize this OLED screen and the two power wires. So the one power wire and the one ground wire going into it. So that's how you can highlight and point to different things. If you would like, you can also go to pen tool and just draw an arrow. And just draw an arrow. Or something along the lines. And you can point to this thing, or you can put a circle on it. Yeah, something like this. It's all up to how you want to design your documentation for submission. So yeah, it's just nice to have, and when you're ready to export, you can just do File, and then you can do Export. And here's the nice part. You can adjust the size of it on the right side panel. You can also adjust your DPI, which is the quality. So if you bump this DPI from 96 all the way up to, let's say, 300, your file will be larger. However, you'll get way higher resolutions. So you won't get blurry holes or blurry text from the Arduino. Because if you have a very low DPI, this A0 kind of just blurs together, this A1 kind of just blurs together. So I recommend having a higher DPI, but don't go too crazy because that'll just ruin your download speed, and it'll be a really large file. So yeah, at least make it a high enough DPI where we can actually read the text. Alright, so that's basically how you would do fritzing for diagramming.